Hi everyone. In this video we're going to discuss reactions at the benzylic position. Alright, so the benzylic position is one carbon away from benzene. So if you have some sort of carbon group coming off of the benzene ring, the first carbon will be the benzylic position. Now, the reason that we can talk about so many reactions at this particular position is because the benzylic position has unique reactivity due to resonance. Okay, so let's start with oxidation reactions. So let's say we start with toluene. So remember, toluene is a benzene ring with a methyl group attached. And let's say we want to turn that into a carboxylic acid. So again, this is all occurring at the benzylic position. So one way that you could do this is by using a strong oxidizing agent like chromic acid. Or you could also use potassium permanganate followed by a weak acid and heat. So these are reagents we've seen before. But again, this is all occurring at the benzylic position this time. Okay, now there are some scenarios where this oxidation reaction would not work. So for example, you might remember that if you have, for instance, a tertiary alcohol and you add an oxidizing agent, there's actually no reaction. Do you remember why? So remember, you actually need to have protons on that carbon in order for oxidation to occur, because you're removing 2 electrons every time you perform an oxidation step. So you're removing that proton and its 2 electrons. So if you don't have any protons at the carbon that you're trying to do the reaction at, you can't oxidize it. And it's the same thing with the benzylic position too. So let's say we have a tertiary carbon at the benzylic position. Again, there are no protons there. So if you did add an oxidizing agent, nothing would happen. So you do need protons at the benzylic position to perform oxidation. So this is stuff we've seen before again. So we saw this in the alcohol chapter, but now we're just applying it to the benzylic position. So let's go over a couple example problems. So in the first problem, oops, my marker changed. There we go. So let's say we have an ethyl group that's coming off of the benzene ring, and we add Na2Cr2O7 followed by H2SO4 and water. So this will make chromic acid. What kind of product would we get there? So if you want to pause the video and try this on your own first, you can. And when you unpause, we'll go over it together. Okay, so first let's identify the benzylic carbon. So that would be the first carbon off of the benzene ring. And let's see, how many protons does that carbon have? 2. Okay, so if we perform an oxidation here, then we're going to end up with a carboxylic acid at the benzylic position. Okay, but what happened to the methyl group here? Where did that go? So what's really interesting about this type of reaction is no matter what carbon group you have, you're going to form a carboxylic acid, and then everything else just kind of gets left behind. It leaves the molecule. So that methyl group just leaves. Kind of interesting. It's like magic. All right, so let's look at another example. This time, let's say we have an isopropyl group coming off of one side, and then we'll have another, let's see, long chain with an alcohol group coming off of the other side. And again, we're going to add chromic acid. Okay, so try this on your own first. See if you can figure out what the product would be. And when you're done, you can unpause the video and we'll go over it together. Okay, so let's find our benzylic positions. So on the isopropyl group, that first carbon is our benzylic position. And how many protons does it have? Just one. And let's see, we also have a benzylic position down below. And how many protons does that carbon have? 0. So that means no oxidation will occur there. But do notice we have an alcohol, and we can perform oxidations on a carbon attached to an alcohol group. And that carbon does have protons. All right, so we do still have 2 oxidation sites. One is at the benzylic position for the first group. The other is actually down the chain at the alcohol. So let's draw what this would look like. All right, so again, we're just completely getting rid of these 2 methyl groups and just forming our carboxylic acid at the benzylic position. And then down below, we're forming our carboxylic acid where the alcohol was. Okay. So this is kind of cool because you can sort of ignore whatever carbon chain there is. And just note that you're going to form a carboxylic acid at the benzylic position. Any other carbons are just going to leave on that chain. Okay, so let's look at a different type of reaction that can occur at the benzylic position. So one reaction we can do is free radical bromination. So let's say we have toluene again. And we're going to add NBS and either heat or light, either one is fine. This will give us a bromine at the benzylic position. So this is very similar to allylic bromination that we've seen before, but this time it's just at the benzylic position. Okay, so what if we have something, oops, sorry, slightly different? What would our product look like? And feel free to pause the video and try to figure this out on your own first, and then we'll go over it together. Okay, so what would our product look like? Well, first let's identify our benzylic position. 1 carbon away from the benzene ring. And we're just going to add our bromine to that same position. Awesome, easy peasy. Now, what's great about this is we now have a leaving group attached. So we could follow this reaction with an SN1 or SN2 reaction or a Grignard reagent. So once you add that bromine onto the benzylic position, you could then maybe add another group in there through substitution or through a Grignard reagent. Okay, so let's actually talk a little bit about substitution chemistry at the benzylic position. So let's say we performed that radical bromination. So we added a bromine to our benzylic carbon. We could then add sodium hydroxide, and this would give us an alcohol. So would that be SN1 or SN2? So remember, with SN1, we would form a carbocation intermediate, right? So what kind of carbocation would we have? A primary, secondary, or tertiary carbocation? We would have technically a primary carbocation, but remember the benzylic position is stabilized by resonance. So now let's look at the nucleophile. Is that a strong nucleophile or a weak nucleophile? A strong nucleophile. So does SN1 or SN2 prefer strong nucleophiles? SN2. Okay, what if we wanted to do an SN1 reaction? What could we use to add an alcohol at that same position? We could just use water. So remember the carbocation intermediate for SN1 is stabilized at the benzylic position due to resonance. So you could do either SN1 or SN2. It would just kind of depend on whether you're using a strong nucleophile or a weak nucleophile, which mechanism it goes through. Okay, so whenever we talk about substitution, we also kind of talk about elimination, right? So let's talk about elimination chemistry at the benzylic position. So again, this is all stuff we've seen before, but we're just applying it to a different type of molecule here. So let's say we have an isopropyl group coming off of our benzene ring. And let's add a leaving group on there. So how could we add a leaving group? What reaction did we use previously? NBS and heat or light. Okay, so that would add a bromine at the benzylic position. So we've got our leaving group. And there's a couple of different ways that we could perform elimination here. So we could go the E1 route, or we could go the E2 route. So if we use the E2 mechanism, we would need a strong base, and we would probably want to use either potassium tert butoxide or sodium hydroxide, for instance. You could also use DBN or DBU in place of potassium tert butoxide. That's fine too. All right, so we would get our double bond on one of those methyl groups. Another option, we could turn that bromine into an alcohol group. So maybe we go through the SN1 mechanism, like we saw on the last slide. Oh, I'm running out of room. That's an alcohol there. And then we could go the E1 route and turn this into a double bond by using concentrated acid and heat. So that's another possibility. So again, reactions we've seen before, we're just applying it at the benzylic position. Now, in your textbook, there's a nice little summary of all of these reactions that we've gone over. And I also posted this as a study guide on Canvas under modules study guides. And this is just a little flow chart. So for instance, if you start with toluene, you could perform radical bromination to add a leaving group. And then you could perform SN1 or SN2 to get an alcohol there. And then you could do all sorts of alcohol reactions. You could also, for instance, now that's a primary alcohol. Or you could, let's see, start with an isopropyl group, form radical bromination, and then go through SN1 to form a tertiary alcohol. And then do any number of reactions there for an alcohol. Or you could produce an alkene and do any number of reactions there as well. So this is a handy chart you can use when you're working on your pod or your homework. And I think we'll stop there today. Next time, we're going to finish up our last chapter of the quarter, and we're going to discuss reduction of aromatic compounds, because here we were really performing more oxidation reactions. But we'll go into a little more detail with reduction, and then that'll be it for the quarter. So you're almost done. All right, I'll see you in the next video.